In the mystifying domain of quantum mechanics, a theory that has captivated innumerable intellects is the concept of Schrödinger's cat. This captivating thought experiment, a groundbreaking contribution to our comprehension of the quantum universe, was brought forth by the ingenious physicist Erwin Schrödinger during the flourishing era of physics in the early 20th century. It was a time when the puzzling conundrums of quantum uncertainty were proliferating, and scientists found themselves wrestling with the profound implications of this new, intricate realm. Erwin Schrödinger, a consequential figure during this epoch of scientific discovery, conceived his cat analogy to shed light on the paradoxes ingrained in quantum phenomena. The crux of this thought experiment roots itself in the innately bizarre and counterintuitive behavior of quantum particles. Contrary to the predictable dynamics of classical physics, the subatomic particles of the quantum world disregarded norms and defied logic, existing in multiple contradictory states all at once. Diving deeper into the origin of Schrödinger's cat, it was a direct criticism of the Copenhagen interpretation of quantum mechanics. Schrödinger intended to demonstrate the absurdity of the existing view that a particle exists in all states at once until observed. He imagined a scenario where a cat is put in triggered by the quantum state of a particle. According to Copenhagen interpretation, the cat would be both dead and alive until observed. This paradox was his way of highlighting the peculiar and inadequate explanation of quantum mechanics. The implications of Schrödinger's cat in the quantum world are profound. It emphasizes the inherent oddity and complexity of the quantum universe, where entities can exist in multiple states simultaneously. This baffling reality is what gave rise to the theoretical structure behind Schrödinger's cat. The captivating concept emerges from the peculiar behavior of particles in the quantum world, further emphasizing the paradox of quantum superposition. The Schrödinger's cat experiment ultimately underscores the clash between our everyday experiences and the strange happenings in the quantum world, pushing us to reevaluate our understanding of reality itself. The double-slit experiment, a cornerstone of quantum physics, displays the enigmatic qualities of quantum particles. In this experiment, an electron appears to traverse two slits in a screen simultaneously, a phenomenon that seems to defy traditional understanding of matter behavior. Initiated for the first time in the early 19th century by the polymath Thomas Young, this experiment served as a monumental proof of the wave-particle duality concept. It showed that matter, such as an electron, could exhibit properties of both particles and waves. To make sense of this peculiar behavior, one can imagine the electron not as a lone particle, but rather as a wave, spreading out and interacting with itself as it passes through the slits. Alternatively, one can also perceive the electron as being in a superposition of all possible paths. This means that instead of following a single defined path, the electron simultaneously explores multiple avenues, and it's only our observation that forces it to settle on one. The concept of superposition is a central pillar of the quantum mechanical framework. It's a term that serves as a linguistic aid, helping physicists to communicate the inherent uncertainties associated with quantum particles. It encapsulates the unnerving principle that any property of a quantum particle, be it its position, momentum, or spin, cannot be known with absolute certainty until measured. This imbues the world of quantum mechanics with a cloud of uncertainty and probabilistic outcomes, changing our understanding of the fundamental nature of Schrödinger's cat, a renowned metaphorical narrative, elucidates the complexities of quantum superposition. The brainchild of this thought experiment is Erwin Schrödinger, one of the luminaries in the realm of physics. This intriguing thought experiment involves a cat, a box sealed from the outside world, and a radioactive atom. The experiment begins with the cat being put in an isolated box, along with the volatile radioactive atom, which is notorious for its unpredictability and potential to decay. Should this atom decay, it sets in motion a series of reactions that lead to the release of a deadly poison within the confines of the box. This poison, lethal to the feline, introduces an element of potential fatality. However, in the absence of an observer, that is until the box is opened to physically check on the cat is, rather paradoxically, both alive and dead at the same time. This is a direct consequence of the principle of quantum superposition, where the cat's state mirrors the uncertain state of the atom, embodying multiple states concurrently. This unique state of coexisting life and death is a bizarre reality in quantum physics, a field that often pushes the boundaries of our understanding of reality. Schrödinger's intention illustration was not just to educate, but to provoke thought and challenge the application of quantum superposition to objects on a macroscopic level. This experiment invites us to question the nature of reality and the limitations of our observation, thus leaving its mark on the philosophical implications of quantum theory. The concept of superposition underpins quantum computing, an avant-garde field that unites the disciplines of computer science and quantum physics. In this extraordinary field, the enigmas and complexities of superposition are utilized to construct a novel category of units, referred to as qubits. These are fundamentally different from traditional bits that exist in a definite state of either 0, 0, or 1. Qubits, on the other hand, due to the principle of superposition, have the potential to exist in numerous states at once. This principle of superposition allows qubits to hold a 0, a 1, or both 0 and 1 at the same time, thereby exponentially increasing the data they can hold and process. In quantum computing, this translates to a machine capable of conducting multiple calculations simultaneously. This unique capability of qubits presents them with a significant advantage over their classical equivalents. They have the power to process vast quantities of data and conduct intricate calculations at an exponential pace. Imagine a single quantum computer performing that would take the most advanced classical computers years to process. This remarkable ability uncovers a universe of computational potential. We're talking about advancements that could potentially eclipse the combined processing capacity of all the traditional computers world. But the implications of these advancements reach further than just speed and data processing. They stand to profoundly transform our understanding of information processing, heralding advancements that could revolutionize not just the field of computing, but also data encryption, artificial intelligence, and even drug discovery. As we explore the quantum enigmas encompassing superposition, a burning question emerges. How does the intricate ballet between particles existing in multiple states and the act of observation mold the very fabric of reality? Indeed, going deeper into the layers of this puzzling theory, we realize the crux of the influence observation has on reality. Quantum superposition is a phenomenon that undermines the established rules of traditional physics, pushing us to reassess our comprehension of the physical world. It suggests that particles can exist in multiple states at once, only crystallizing into a definitive state when observed. This is where the role of observation becomes key. In the quantum world, it seems that the simple act of observing can determine reality. It's as if the particles are waiting in a state of uncertainty until they are observed, at which point they choose their state. This mind-twirling concept leads us into the domain of Schrödinger's cat, a thought experiment that mirrors the extraordinary nature of quantum mechanics. This thought experiment illustrates how a cat, sealed in a box with a radioactive substance, can be both alive and dead until observed, mirroring the superposition principle. The enigma surrounding this paradox intensifies our fascination with the quantum world, stirring our wonder about the limitless possibilities that dwell within its dominion. The broader implications of quantum superposition propel us towards introspection about our universe and our role in it. As observers, we are central in sculpting its complexities. This brings us to a pivotal question. Is it our observation that crafts reality, or does reality exist irrespective of our observations? Questions leave us marveling, reflecting on the expansive mysteries of our cosmic home. Until next time, stay curious. Now, let's take a journey back in time to hear from the man who started it all. We've got a rare footage of Erwin Schrödinger himself discussing his famous thought experiment. Voiceover. Here we see Schrödinger, the Austrian-Irish physicist who proposed the thought experiment we've been discussing. Listen as he explains the paradox of his theoretical cat, both alive and dead until observed. Voiceover. As you can see, even Schrödinger himself was baffled by the implications of his own thought experiment. He was pointing out the strangeness of the idea that observation could alter the state of reality. This concept, while mind-bending, is a cornerstone of quantum mechanics and has sparked countless debates among physicists about the nature of reality. It's important to remember that Schrödinger's cat is a metaphorical illustration meant to highlight the paradoxes within quantum mechanics. After hearing from the originator of this thought experiment, we are left with even more questions. How exactly does the act of observation collapse the superposition? And why does it behave this way? As we delve deeper into quantum mechanics, we continue to uncover more questions than answers, but each question brings us one step closer to understanding our complex universe. Until next time, stay curious and keep wondering.